Welcome! In this video, we'll be showing an AI beating the popular 1988 arcade game Double Dragon with a model trained within Red Hat OpenShift AI. Here, we have over 100 instances of Double Dragon being played within OpenShift AI. It's running through a variety of different randomized actions and then optimizing on those actions to learn to beat the game. Let's dive into how we made this possible. We're going to use a form of machine learning called reinforcement learning, or RL. This is a form of machine learning where we take repetitive tasks over and over again and find different patterns and optimizations through training the model. This could be through different random events, or in our case, we'll have different rewards where we tell the model when it's performing the way that we are expecting and ways that we don't want it to function. Let me show you some examples of this. Let's start within our notebook and show a few ways that this AI model was trained and some of the different parameters and configurations that went into the training. Here we have a variety of different packages that are being pulled into Python to train this model. Most importantly is the baseline 3. This is the machine learning library that we're using to train the AI to ultimately beat the Double Dragon game. Through this, we're bringing in a popular training algorithm called PPO. We also use the popular Gymnasium library, which I'll show you more here in another script. Now let's show the initiation of the Game Boy environments that will play concurrently and attempt to beat the game. We have a few helper functions here, but the primary function we're most interested in is this make environment. This will create a variety of different instances of the Game Boy emulator PyBoy. We'll also configure it in this case in what we call a headless instance. This way, I don't need to hear the sound or the visuals. This keeps the memory down and allows us to have more instances to train the model. We have a variety of different configurations here that we pass in to the Game Boy emulator. The action frequency here lets the Game Boy emulator know how many frames should it have before each action is taken. This is critical as sometimes you want actions to be a little bit longer, and if certain actions are done too quickly, it may not even be registered by the game. In this case, I found that the 8 frames is the sweet spot between the length of the actions and how frequently we want actions to be taken. To speed up the process, I have loaded in a save file that ignores the first cutscene. This allows the emulator to jump right into where the action starts and helps speed up the process. We also have here max steps. This correlates to the amount of actions that are taken. At the point of the maximum steps, the emulator will stop running to prevent an infinite loop from happening. I have a variety of other configurations, but those are probably the most important to go over. We now set the amount of CPUs that will be used for this particular run. In this case, I have it set to 10. For every CPU that's set, we'll have an instance of the Game Boy emulator running on that particular CPU. In this example, I just have one workbench that will be running this in a vertical fashion for scaling. But there are ways that we could configure this with tools like kubearray or Codeflare, where we could distribute this across many different nodes within OpenShift AI. Here, we'll go ahead and loop through and create the necessary environments we need, and then we'll set up a callback. This is a way that we can set checkpoints where we can verify if the results are what we're expecting. This is a good way to keep certain records of instances through the training. There may be a point that you make a change that you don't like. You then need to be able to roll back to a particular checkpoint. This is a good way of showing how that's possible within OpenShift AI. Let's go ahead and start these instances. We'll come up here and play this cell. All right, our 10 instances are now ready, and let's go ahead and start the model training. I have two options here. I can start from a checkpoint if I provide a file name, or we can start a fresh training session here. For this video, I'll be showing a fresh training run. You'll see here that I don't have very many parameters when starting a fresh training session. I typically like to take my checkpoints after a few iterations of training and then try to apply different hyperparameters to my model. Let's talk about a couple of these. Here I have the gamma. Gamma is a way to let the model training know how much variety I want to take. Let's say that the model has found a way to go through a particular door within the game. But let's say maybe that was the incorrect door. Maybe ultimately we needed to use the right door instead of the left door. If we're not training the model appropriately and setting the right gamma, it may get fixated on that one point. In this case, this would be the overtraining of that particular run. By allowing the gamma to be a little bit lower, we can have some variety where the model will try a few different variations throughout the training course. Ultimately, this can lead to higher runtimes and more iterations, but the quality of the output will likely be better. Eventually, you may like what you're seeing in the output of the model, in which case you may bring up this gamma a little bit more to make the variations less to try to refine the process that you currently have. You'll also see here that we're using the CPU in this case. For this type of model, you only get a marginal improvement by using a GPU. So to keep costs down, in my case, I'm just going to leverage the CPU that I have. But there may be some longer models or different types of machine learning training models where a GPU will be more beneficial. So if I wanted, I could come here and specify that I want to use a GPU. I'm also logging out all of our metrics into a TensorBoard log file. Let's go ahead and start this training run. You'll see here the training has started, and we specify that we're using the CPU device in this case. It's going to take a few moments to start getting some results back. At most, we'll have the episode length here for the maximum amount of steps that are going to be taken within the game. You may see some earlier instances, though, of results, and this will be the case where the playing character has died 3 times and has lost the game. Let's go ahead and take a closer look at a training run. This is a video of me going from the 10 instances up to over 100. We have a few things that we'll take note on. First off, you'll see that most of the frames have certain trends that are happening. The majority of the time, we'll see maybe 80 or 90% of the instances following a very similar path. But let's go ahead and look at some outliers. First, we see here that the playing character is eventually getting stuck here. This is preventing it from moving further on in the game. We need to find ways to penalize the model in this case and say getting stuck is a bad scenario. We can do this in a few ways, and I'll show some of those here shortly. Now, let's move to another section where the playing character is actually progressing very quickly through. We'll see some trends forming. Oftentimes, the character will punch backwards. It is found the optimal solution of beating the different NPCs in the game. I shared this video with a speedrunner recently, and he thought this was very interesting, as oftentimes the speedrunners will do the exact same thing to get through the level quickly. The AI in this case has found the optimal path through the first level of the game. We'll see in this particular frame that the character has now gotten to the first boss. In this case, it's going to lose because it hasn't found the optimal pattern to beating the boss in this case. We'll need to change the reward system slightly. First off, ideally we want more of these instances getting to the final boss so that it has more playthroughs at that point in the level. We can also change the rewards on how it optimizes certain moves, like the back punch, to beat this particular boss. Let's dive into that more. Before going back to our Jupyter notebook, I want to show this particular image. It doesn't look like much is going on here. It's kind of a blurry image, and there's not much that we can make out, with our human eyes at least. But this is actually what the model sees on each frame of the game. We have reduced the resolution and changed some of the pixel structure to optimize the training within the model. A lot of times, high-resolution images are actually a detriment. They take too much information. It's too complex for the model to figure out. This is a process where we've normalized the data into a way that's optimal for this particular algorithm and the training of this model. You will also see that there are 3 images here. This helps the model have some context of its previous moves. The top frame is what's happening now, and then the previous 2 on the bottom are going to be frames from what had happened just before. This allows the model some flexibility, especially when jumping over an object in the game or having to use a ladder or interact with an NPC. This is a way that we can add memory to the model. Now let's go ahead and look more at the reward system. I provide rewards for 5 critical areas in the game. We have score. So this is what happens when our playing character either punches or kicks an NPC in the game. There's a certain amount of score that's assigned for kicks and punches, and then as the game progresses, those will increase in magnitude. We then have position, or in this case, I have it labeled as POS. This turns out to actually be the most critical of all of the reward metrics that we're tracking in the game. By having a reward for each new frame that we have in the game, it encourages our model to explore. It turns out in these types of reinforcement learning models, exploration is the most critical aspect. Sometimes you can even ignore things like score altogether. Every time that the playing character goes into a new level, so the boss, or after it's beaten the boss, I also reward it on top of the positioning. This makes it so that the AI model knows how I want it to progress through the level and not get stuck in bizarre scenarios. Lastly, I penalize the AI for losing lives. This makes sure that it tries to conserve its health throughout the level and finds optimal ways of beating the NPCs. Another way I've optimized the game is by removing some unneeded actions. You'll see here a list of the actions that are available to the model. These are the actions that it starts off doing randomly and then eventually forms patterns on as it progresses. What's most important here is that you'll see that I have removed this button B. In this case, that's the kick. In this version of Double Dragon, the kick is not an optimal solution for getting through the level. By removing this particular line, I optimized the playthrough by over 30%. Now let's go back and look at our model training. You'll see here we're starting to get some results back. Let me unpack this a little bit. Here we have a variety of different instances and the score. Score is probably not the most important metric here, but it gives me an idea of how the playing character is interacting in the game. What's most important to me, though, is the final level that it got to during this playthrough. You'll see here that we're starting at 1, but then here we actually have a level 3. This is where it takes on the first boss. We showed an example of this in the previous view, where we had many different iterations of the game playing. This is where I've had to tweak the reward systems, as I mentioned, to get more of these getting to level 3. Now that we've done a few run-throughs of the game, let's go ahead and look at some metrics. We can use the popular tensor board to visually see these metrics within our Jupyter Notebook. We'll go ahead and start a session. If you come in here into our scalar section, we can see some more graphs. We'll see things like FPS, the KL, different clip fractions, our entropy loss, some variance functions, and the different loss functions here from the metrics that are collected. This is a good way for people who are doing model training to see how effective their model is in the different training cycles. I want to quickly show the Docker file that we use to make this workbench possible. Here, I take our OpenShift AI Jupyter Data Science Here, I take our OpenShift AI Jupyter Data Science image, and then I go ahead and add some things to it. Let me show you the requirements file. Most importantly here, I'm adding in the PyBoy package. This is the emulator we use to run through the different iterations of the game. But this is an example of how we can take a base image within OpenShift AI and add the necessary packages we need to run our experiments and our model training. After making some adjustments, specifically removing the kick and also increasing our positional rewards and decreasing our scoring rewards, I was eventually able to beat the first level of this game. As mentioned before, eventually the AI learned that punching from behind, so using its elbow, was the most effective way to go through the level. It goes through very quickly by finding a corner and then letting NPCs come to it with his elbow move. Eventually, he'll make his way into the boss battle, where he'll do this very same move, but make sure to position himself in the corner. And you can see here, he finally beats the boss and moves on to the next mission. Now, here, I've had to train it in a variety of ways to use these ladders. This is where vertical positioning was critical, and making sure that it knew how to jump effectively between platforms. That's for another video. That's it for this demo. We've shown how reinforcement learning can be run on OpenShift AI. Now, this is a cool and fun example, but what are some practical applications of this? Well, this same type of model is used to train things like driverless cars and robotics. There are a lot of applications for this particular field of machine learning, and also how it relates back to things like generative AI and large language models. I'd like to give a special thanks to Peter from the Pokemon RL community. Here is a GitHub page of a Pokemon version of what I did here today. Peter has examples of a PPO algorithm training a model to beat Pokemon Red. A few things I want to call out here is that he has an amazing video on YouTube that outlines the process and gives you great visuals of how the model played through the game. Lastly, there's also a Discord community where we discuss things like Pokemon, but also a variety of other games like Super Mario Bros. Do check them out. Thank you.